Sustronics, sustainable and green electronics for circular economy.
Hello, everyone. Good afternoon. So you are now warmly welcome to this Sustronics webinar on sustainable and circular electronics. And this is broadcasted from sunny and warm Barcelona. And for your information, the webinar will be recorded so we can share it afterwards in our website and YouTube channel. And we have an interesting agenda ahead of us today. We will especially focus on how the various sustainability aspects can be addressed horizontally with a couple of technology examples. And I am myself, Liisa Hakola, a senior scientist from VTT, that is the Technical Research Center of Finland, and I'm also the technical manager of this Sustronics project. And today I will be chairing the webinar. And we will first hear all the presentations, and then afterwards they will be followed by a joint questionnaire session. And if you want to ask questions from the presenters, please type your questions to the chat and I will facilitate the Q&A session in the end. But
we can't hear you. You are mute. Your mic is mute.
Okay, good
now
that someone pointed that out.
Right.
Okay, so I'll start from the beginning. So welcome to this Sustronics webinar on sustainable and circular electronics, and we are broadcasting this live from sunny and warm Barcelona. And for your information, the webinar will be recorded so we can publish it later on in our website and YouTube channel. And today we have a very interesting agenda with several speakers from the project. So we will focus on how the various sustainability aspects can be addressed horizontally. And we also have a couple of technology examples. And I am Liisa Hakola, senior scientist from VTT, that is the Technical Research Center of Finland. And I'm also the technical manager for the Sustronics project. And today I will be chairing this webinar. And we will first hear all the presentations, these ones, and then it will be followed by a joint Q&A session. So if you want to ask any questions from the presenters, please type them in the chat and I will then facilitate the question session in the end. But I would now like to first invite the first speaker, Ramon Kaanen from Philips. He is our Sustronics coordinator. Welcome.
Well, good afternoon and very welcome from myself as well. And thank you, Liisa, for kicking it off. So on Sustronics, I want to briefly give you some overall presentation on what is Sustronics in the broader sense about. So to do that, let me first start here. As you can see on this slide, Sustronics, it's a large consortium combined with larger industry firms and enterprises, small medium enterprises, research organization, universities, actually throughout Europe. And you can see it's actually, it has a big geographical spread. There's over 40 partners, 46 partners participating in over 11 countries. The total effort of this program will come to approximately 3,000 hours, months, sorry. And we are at the closure actually of a 3 years program. Here you can see in a very quick snapshot all the companies, partners of this consortium. You can look at it at your leisure at a later time, but it just shows it's a really big group of a lot of knowledge and experience coming together here. This is also what it looks like. So of course here you see let's say most of the people that have been joining in the end and actually contributing to the things that you're going to see today. Our ambition has been and is to become the European flagship project for sustainable electronics. The way we want to achieve that is by building an ecosystem to demonstrate how electronics industry can benefit from, for example, sustainable materials, sustainable manufacturing of those materials, eco-design guidance, energy-efficient products, and circular business models. To translate that more into the objectives that we set ourselves, so we promised ourselves and our sponsors, also the European Committee, to deliver on improved resource efficiency, functioning sustainable electronics, quantification of those sustainability metrics and other metrics, new metrics, supported and validated through, in the end also, like I said, the quantification of everything we do, how to deal at end of life, how to bring that back to design, and to bring all of that together in our pilot approach. A bit more detail about what we've really been doing in this consortium. Here you see basically the full scope. I won't spend too much time. There's a lot of content here. But you can see we've taken a pretty holistic perspective in addressing this topic of sustainable electronics. A lot of the research has gone into material development on, for example, bio-based substrates, adhesives, inks, and others, and to provide functioning alternative materials into, for example, components and devices, also based more upon eco-design principles. And when I say components and devices, you can think of sensors and inducers, energy storage, energy management, wireless communication and energy harvesting, hybrid and integrated components, and software functionalities. So a very broad scope. And in the middle there, you see manufacturing. So that combines both more sustainable manufacturing practices for at the material level, so at the process level for that, as well as for component and device level. We've been bringing that together, and that's, I think, a core element of this program into end-use cases and pilots. I'll tell a bit more about that in a second. At the bottom, you will see everything we've done. We've been validating and proving through, for example, LCAs, also testing and creating new value creation options, propositions, business models, and also bringing into scope end-user engagement in to understand the impact of what we're doing. So you see it's a lot that we've done, but I think we've also gotten pretty far with all of it. So here you see how all of this came together. You see we've had a big work stream working on sustainable materials, another work stream on sustainable manufacturing and components. And you also see at integration, it comes together, feeding into these end users, validations and pilots. And like I said, at the bottom of it all, everything we've been validating through our sustainability assessments and also testing the circular business model impacts of that. So more about these pilots. So we've had 10 pilots running, and we basically clustered them in 3 categories. We call them use cases. So the first use case has been focusing mainly on redesigning existing products in line with circularity and sustainability requirements, while also addressing opportunities for new circular value propositions. And the application focus of these 3 pilots has been mainly on health and lighting. The second use case category has been on sustainable manufacturing for electronics. So this has been focusing on transforming existing products into environmentally friendly alternatives while maintaining the device functionality, specifically focusing on utilization of bio-based materials together with sustainable manufacturing concepts. The application focus of these pilots has been mainly on wearables, diagnostics, and automotive. Last use case, focusing on environmentally compatible single-use electronics, a challenging topic from sustainability perspective. In these use case pilots have integrated sustainable technologies that are compatible with end-of-life management strategies such as composting, biodegradability, and recycling. The 4 pilots represent innovative sustainable technologies, coming with benefits even beyond sustainability, such as remote diagnostics and preventive health. Sorry. Then, how did we get in the end to the end results? we've had 3 generations. We are now at the end of the 3rd on evolving integration and also proving, let's say, the outcomes. And from generation 1, where we were baselining and target setting, we moved in generation 2 to lab scale integration and performance validation. And finally, where we are now, we are looking at fully validated demonstrators based on pre-production batches. And you will see some of that today. And then, as my last slide, this is a snapshot of what that looks like in the end, the outcome. You can see real, tangible examples here of the outcomes of all this work coming together in these pilots. So with that, we will show you more of that, what's behind this in the other presentations. And I want to hand over to the next speaker. Mikko from ScreenTech. Mikko, go ahead.
Yes, thank you, Ramon, for the nice introduction to Sustronics project. Next, indeed, we have CTO Mikko Paakkolanvaara from ScreenTech Oy. He has been working with electronics manufacturing for the past 22 years, and he has focused on printed electronics, R&D, product development, and manufacturing. And for the past 7 years, he has focused also for the medical electrodes. He has Master of Science for Electrical Engineering and Bachelor of Science for Biomedical Engineering from the Oulu University. Welcome.
Hello, everybody. Yeah, so first I want to start with printed electronics. So most of the pilot cases we had in this project had somehow printed electronics involved in the manufacturing process, how the pilots were manufactured. Printed electronics mean generally that we print conductive and dielectric layers on some sort of substrate, which is typically flexible and sometimes also stretchable, like plastics, PET, and TPU. And these circuits, this generates a circuit which works like PCB, which is typically the base of different kind of electronic devices. Printed electronics is an additive and quite simple method to do. So we add material only on those locations where we want to have them, which make this also quite much more sustainable process if compared to the PCB industry's chemical intensive low power etching method in the intensive chemical etching processes. Suitable use cases for the printed electronic products are typically large area devices, single-use devices, stretchable, and also low-power electronics. And a thing of these disadvantages of the printed electronics compared to PCBs is that they have higher resistance, which means that they don't suit for all high electrical performance devices, and also that the printed electronics manufacturing methods are still evolving, so they are not fully mature as the PCB industry. On the pictures below, you can see, for example, sample of the PCB with some components integrated on that, and also the same on the right side with printed electronics. And in the middle, you can see that how the comparison of product impact of various LED strips shows in terms of kilos of carbon dioxide generated when manufacturing one LED strip on the left with traditional PCB, and on the right, printed LED strip with copper paste. Then 2 of the pilots on this product were focusing more also on medical electrodes for health monitoring. And that means that there is kind of sticker which you attach to your body to measure, or in some cases also simulate a signal to your body in order to measure or stimulate something. And typical biosignal measurements are, for example, bioelectrical impedance analysis, electrocardiogram, electromyography, and electroencephalogram for brain measurements. And the focus on these 2 pilots was to generate 3 different kind of medical electrodes and make them more sustainable. Currently, more or less all custom medical electrodes are made using fossil-based plastics like PET or TPU, and then silver-based conductive paste for the conductive patterns what are needed there. And this same applies also to most of the printed electronic solutions, not only for the medical electrodes. Medical electrodes are typically single use, so it makes sense to make them as sustainable as possible because you typically throw them away after you use them. And it's also a fact that the number of medical electrodes used in the world will increase in the future because of aging of population, lack of healthcare resources, and also remote healthcare, which is increasing around the world, as well as health awareness of people in general. And if comparing the fossil-based plastics plus silver, it makes the global warming potential, as shown in the graph here, in a similar structure quite high. And if we compare a paper-based substrate with copper or carbon-based conductive patterns, it generates much less global warming potential, which is very attracting in order to make more sustainable products. And yeah, the question basically was in this project that is it possible to make more sustainable medical electrodes? And we were focusing to make them more sustainable, but also test that they are functional so that they work for the purpose what they are meant for, and that they have a proper wear time so that it can be used for the intended use, and also that what is the price difference between the existing product stacks and the developed one. So we basically have 3 different electrodes, what I go through here. First one is bioimpedance electrodes. So in the final phase, generation 3, we generate 27 different variants using different kind of conductive pastes, different kind of substrates, and also different designs in order to find out that what is the best outcome from these. There were some comparison tests made against the Polar H10 HR sensor and the respiration belt to find out the functionality and usability of the signals which were measured, and also to see the differences between the variants. On the pictures, you can see some of the variants that were made and also the setup for the measurement. And in the end, it showed out that the variant printed using the design A on this generation 3, using paper with copper paste or carbon paste, was found that it suits well for the measurement purpose it was meant for. The other one was EGG electrode. There we had 11 different variants made with different paper substrate and carbon paste combinations in the end. Here we didn't use copper paste because we found out that it doesn't work so well. And then we make a comparison to commercial EGG electrode sold by Mosense. And there you can see on the pictures some of the samples made and also what happens when you are sweating a lot or taking a shower with a paper-based medical electrode. So it wets the paper and it generates that it doesn't work so well and basically rips apart in the end. However, we managed to make a variant, a couple of them, on a paper substrate and with carbon-based combination that it works well when comparing with the current commercial available electrodes. You can see here, well, not too well, you can see here some graphs of the measurements made. If comparing the sustainable one, there were some irregularities in the signal 2 to 4% of the time, but anyway, something that could be used for the purpose again. The third one was EEG electrode, so to measure brain signals. There we had 15 different variants on the final phase, and they were manufactured with different kind of conductive paste again and different kind of substrate. And the comparison test was made against gold standard electrodes from Kendall, and it was found out that the functionality and the usability of the measured signals was good especially with the one sample made with the paper and copper paste. If thinking of the sustainability, then there was also a life cycle analysis made for these, which showed that as predicted, the carbon and the copper paste are more sustainable, and also substrate used are more sustainable than the fossil-based PT. And the comparison of the benchmark electrode and the generation 3 electrode for EEG measurement shows significant improvement across all environmental impact categories, which you can see on the graph here on the right. There are also several other materials which are needed on the electrode materials, which need to be taken in consideration. Here the summary. So basically, sustainability that we could achieve on all 3 different electrodes, that they are more sustainable. Functionality, it works well for bioimpedance and EEG, and also it works good enough for ECG. The wear time, we see that below 24-hour wear time works well with the samples what we have made here. 2 hours, 1 hour work time works perfectly, but then with the 24-hour and lots of sweating, it doesn't work so well. And what is also interesting for most product owner is the price, because you can achieve these with a 20% cheaper price than with the current material stack. So based on the results, the new material stack works and has sustainability and price benefits for use cases with less than 24-hour wear time. And then what next? So basically on our factory, music, let's put it away. So on a factory in Finland, we are capable of doing this manufacturing already on paper, on roll-to-roll process, printing copper paste on it, and then we end up having finally some electrodes which are made on paper using copper paste and which are suitable for EEG measurements. Thank you.
Thank you, Mikko. And indeed, a reminder, if you have any questions, write them in the chat and they will be presented in the end. Our next speaker is Associate Professor Ulla Saari from Tampere University. She holds a Doctor of Science degree in Industrial Engineering and Management, Master of Science degree in Environmental and Energy Engineering, and MA degree in Languages and Social Sciences. Her research focuses on sustainable industrial transformation and innovation related to industrial product and service systems, especially within a circular economy. Welcome.
Thanks a lot for the presentation, and it was really good to have this use case, pilot case presented before, so we can talk about the big picture here a bit. So we had a work package 4 in Sustronics focusing on building business models and looking at the sustainability. And I'm like the first speaker now here of this work package 4, and I will be then followed by people presenting the LCA methodology more, and also looking at the end of life management as well as the eco design process. So I'll just launch off this work package 4 presentations here. We had the great opportunity to join this with a doctoral researcher who has been focusing in her work on circular business models for health tech industry, which is very demanding sector. So it's resource intensive and there's a lot of waste generated in that sector. However, we have the opportunity to create more new kinds of technologies that are less invasive and are really good for then taking care of patients. And we have to figure out a way to do it more sustainably. So with this kind of a circular economy concept, as you can see in this picture, which is still very valid, even though from 2016. So the whole idea here is to keep products in use as long as possible. If there is an opportunity to perhaps refurbish, use it again some way, it's more sustainable than just then taking a new product into use. So especially those parts that are not touching the patient's body, you can do it easily. So all this thinking of this has to start in the beginning of the product design phase. And that's what we've been trying to figure out together with the pilot cases, how to do this in a way that actually then also serves the functionality. So we of course have to have products that are functional, but are also sustainable. And finally, then the last option would be then to recycle or then throw it away. And of course, we have to accept that in the health tech sector, that there are also those kinds of parts that have some kind of a toxic, maybe chemicals, or then some bodily extracts that you have to then burn it. But still, we're trying the best to do more sustainable products. And the way we approached in actually this Sustronics was starting off with thinking about the elements in a typical business model and trying to circularize, if you can say like that, the value proposition and the way we deliver it, create it, and then capture the value. So we have to have these elements of, in addition to environmental, also the social and economic factors that build a business model. And we started off then looking at one by one. While this was happening, of course, the pilot cases we're working on. So it is a kind of a process of concurrent engineering, I would say. So you have this horizontal way of working. There are developments in the technical side, but then you start thinking about the way that you are serving and creating value and improving the product so that they, in addition to answering to the needs of the patients or customers, that you are harming the environment less, using less materials, or somehow circulating them in the value chain. And this means also the opportunity to create less waste. You think about also logistics, even maybe, how to bring materials from closer parts of the world and having the repairability designed in itself in the products. And so when we're thinking also about the whole value creation, we have to also look at the roles in that value chain and the processes. So we had in the Sustronics also this sustainable manufacturing focus, and here the processes can be made maybe a bit more efficient or lean, let's say. So that's also something to think about case by case. And then finally, there is the opportunity for this value capture that you are actually somehow reducing costs. Now think if a patient can stay longer at home instead of traveling to the hospital. And in many cases, some of the products actually had a digital component that allowed to the patient to stay home and doesn't have to travel back and forth to the hospital, which saves everyone's time. And it was actually a very nice finding that with digital elements, we can create more value and more sustainability in that sense. And I actually included here a table, which may be a bit busy, but let's go one by one through, showing a bit how then under the value proposition, you can think about product and services. So you start off with like a typical product design of having the materials more sustainable but in addition to that, you could also think about the way it is repaired, or if there's the additional possibility to track somehow the maintenance cycles to keep it longer in use. So all of this needs to be done also up front when the product is designed. And it's not an easy task, but it comes then naturally the more you do it. And I hope from the use cases and pilots, the companies have realized new processes and ways of working. For sure we have, and we hope to bring it to our teaching as well in our university in Tampere. And when looking at the actual value creation, you also have to think about the customer needs very closely. And it might be that actually a value element might be the savings the customer has or the patient has in the use of that product. So I just brought the example of the patient care element. So if you can stay home longer and don't have to travel back and forth to the hospital, and you have your digital tool or your mobile phone where you can check your scores for whatever meter or sensor you have in use, it's more handy then. And also then about the packaging, distribution, critical elements. So there's a lot of actually EU level calls for more sustainable packaging, and that we also brought up in the pilot cases. It was measured, and you will hear more about that in the next colleagues speaking. And then the circular business modeling. So here the stakeholders, the end users, are key to bringing it into life, let's say, and deploy and implement them. So you have to understand their ways and practices. And actually, we're starting a new project now in Tampere University where we're looking more like the end user focused kind of circular business model innovation. It's a bit of a continuation from this. And then finally, if we go to this processes side, then in the phase when you actually have to take something out of use, if it's a bigger machine, or like we had one case, this imaging machine, you can take parts of it and remanufacture, use it in another kind of a use later on, and look at closed loop supply chains. Very important to think also in the beforehand, before you start implementing the products. And then all the revenues and costs. This was, of course, a bit challenging to calculate in these use cases because we didn't come to that level of technical readiness yet, so that they would have been commercialized. But we had this approach of trying to kind of showcase product as service concepts, or leasing or subscription models. And then finally, the cost element. So of course, initial costs, investments need to be done, but as you get more into the practices and do these processes into the companies, becomes more sustainable in the long run, also economically. And finally, actually, I have just a couple of minutes left, but I would just like to show an example of the work that our doctoral researcher Fateme Habedi did on these kind of archetypes and mapping different kinds of creation of value. So these are a bit long names, but you can here get the sense of how a bit different they are depending on the use case. So you have this digital therapeutics, and you might have wearable health devices with reusable parts, single-use parts, and then this subscription-based functionality. And the way that the design of these started off is you start kind of thinking of the possibilities to do some cycling or reuse and the readers. So we saw in the pilot cases how from generation 1 to generation 2, there happened a lot of innovation on these topics. So you get the first functionality, and then you start figuring out if there's a possibility to reuse and take back. So this is something we also learned, that you have to really have the functionality first, and then you start figuring out these. And then the intensifying thing. This was super interesting because we're talking about electronics, and then this opportunity for digitalization and using the kind of information and data you collect from different components into the healthcare system. So there's the intelligence and the data processing behind that. And yeah, so thank you. I think I used up my time now. So yeah, I love the project. So thank you.
Thank you, Ulla. Yeah, we have also loved to have you in the project to bring this different perspective on sustainability and circularity. Okay, our next presenter is David Sanchez, a researcher from Fraunhofer Institute für Zuverlässigkeit und Mikrointegration. He has a background in environmental engineering, and for the last 6 years he has specialized in life cycle assessment of electronic components and modules, participating in both industry and research projects. Welcome.
Thank you, Lisa, for the presentation. And don't worry, I also cannot pronounce the name of my institute. Thank you to the people who are here and people online. I hope I'm looking at the camera right. So yeah, I'm going to be telling a bit about lifecycle assessment in our project. But basically, first, maybe a short introduction in case anyone is not fully familiar. So what's lifecycle assessment? Long story, very short. Lifecycle assessment is basically a methodology to estimate, quantify the environmental impacts of a given product or service throughout its entire life cycle, hence the name. Technically, you can also focus in specific life cycle phases, but originally it was conceived to have sort of like a life cycle outlook. And maybe a more interesting question is, well, why have we used it in the project and what have we used it for? So basically, lifecycle assessment has been a tool that has helped the different pilots developed in the project to include sustainability in the development process of the prototypes. And we've done that basically by first identifying the so-called environmental hotspots, which basically means generation by generation in the different prototypes, identifying what's driving, what materials, component parts are driving the environmental impacts. And when we find the challenge, then we find the potential solution, finding eco-design pathways to try to ameliorate or avoid completely said environmental hotspots. So in the next handful of slides, I'm going to be giving a brief glimpse of different examples of how different pilots have been finding these sort of eco-design opportunities throughout the life cycle phases. And with that, we start with materials and supply chain. So basically what's in the product. In the graphic on the left, you can see an example of how a pilot could achieve certain reduction of the environmental impact of the production through choosing different materials. So the gray, the biggest part of in this case, we're talking about like a luminaire, a lamp. And the first example is substituting the housing, which originally was metal, for a bio-based plastic that has a lower environmental impact in the production phase. But also in orange, you can see the diffuser, which was originally based on, fossil-based plastics, was substituted by a cellulose-based diffuser that makes the contribution to the production impacts almost negligible. And last but not least, we can also see, as Mikko already presented earlier, substituting a conventional PCB for the LED strip and the electronics with a printed version also achieves certain reduction. But sometimes that's just not technically possible. So we've also seen that, for example, copper inks have lower impact than the silver inks that are more commonly used for printed electronics, but sometimes the copper ink just doesn't have the conductivity or the printability that you need in your application. But there's still options. As you can see in the graph to the right, different substrates and inks are compared, but not only different materials, also the same material, but sourced from secondary sources. And as you can see, the first and the second columns, just by substituting virgin PET for recycled one, totally or partially, as well as the silver for the ink, can already achieve significant reduction with the same material, let's say. Moving on from materials to design, that is how we put the product together. The two examples that I wanted to bring here are the first one to the left is talking basically about modularity. This is particularly important for single-use devices, which some of the pilots were, as you've seen before, because basically everything that you dispose of, you have to produce anew. And therefore here modularity can play an important role in avoiding that the cumulative effect of these single-use devices grows and grows by making, instead of a monolithic single product that is disposed every time, making it modular, two parts, the part that you dispose of every time, making it as simple and minimalistic as possible, and the reusable part is where you pack as much as the electronics as possible so you can keep using it and using it. And this is an example of a personal hygiene prototype. And here we are comparing two different versions, one with higher modularity, one with lower. And you can see that the cumulative effect is lower when you keep as much as the product in use. And the other example, it's similar but a bit different. It's rather designing around the problems. So sometimes you can actually find out ways to just not have the problem completely. The example here is basically a sweat sensor, a sweat patch that basically has to detect the presence of sweat. An older version of the prototype did it with electrodes, but the subsequent version found out that they could detect the sweat also optically, removing therefore the need for electrodes altogether and designing around the problem rather, which also has a positive effect in environmental impact. But moving beyond the product itself, we can also look into the use phase because there is also some potential for environmental improvement. And here I wanted to talk maybe a bit more about indirect improvement, meaning not improvement of a given product itself, but rather improvement of other products and services through the employment of a given product, right? So basically the first example is a point of care C-peptides analysis, so a test kit. And here the point is that you can improve the environmental performance of a test by providing a more efficient way to do it. So in this case, by providing point of care testing, you can potentially remove the need for high impact transport. This is of course highly dependent on the real case with which you compare, but the potential is there. And the second example is sort of similar. It's about the smart wound dressing. where actually you can tell when the wound dressing needs changing without having to remove it every single time, which could lead, especially for not so severe wounds, to lower frequency of changing, and therefore less auxiliary material, less transport, and that's what you can see briefly in the graph to the right. And last but not least, end of life, in which usually in terms of life cycle assessment, end of life, especially in electronics compared to production, doesn't tend to have too big of a part of the pie. However, here the devil is in the details, because again, the impact is rather indirect, namely what we're losing. So in the end of life, the key is rather to make it not the end of the life as much as you can, namely closing the loop. And here you can just see a very rough comparison of different end-of-life scenarios. On the top of the graphic, you see the negative impacts, that is the environmental impacts of the different activities that are required in each of the cases. And the lower part, you see what in LCA jargon is sort of called the credits. So basically the indirect benefit of not having to produce something because you recovered it through recycling. And here, just the point is that, different end-of-life pathways can recover different materials. And eventually the ideal would be all the way to the right to even recover full parts of a product that can still be used. But here, of course, this brings us back again to design, because depending on how you design your product, namely how easy or difficult it is to bring apart the different valuable parts, some of these doors may be closed to you, which means that end of life is not only an LCA question, it's also a technical question and design question. And we will learn more about the recyclability of printed electronics based on the findings on the project in the next block. Thank you very much.
Thank you, David. Now we have a next presentation by Dr. Margriet de Kock from TNO Holst Center. She has a PhD on synthesis of electroluminescent polymers, and she has worked for 10 years in Philips research on materials and applications of OLEDs, and in 2008 she joined TNO to develop multifunctional hybrid printed electronics for textile integration, automotive and healthcare applications. And she has a strong motivation for making electronics more sustainable. Welcome.
Thank you, Lisa, for the introduction and the opportunity to share our work on end-of-life management of sustainable electronics. As you can see from the picture, we're diving into waste bins a lot, and I hope to share what we learned. I will tell you about the compatibility of the printed electronics that were developed with the current waste streams. What are the new opportunities for sustainable printed electronics? We did a study on the biodegradation potential of printed electronics. So I hope to end with the conclusion that surfing the right waste stream with electronics is actually the right title of Sustronics. Like mentioned by the previous speakers, of course, we want to reuse, refurbish, keep the products in the loops and make them as circular as possible. But at some point in time, some point in the life cycle of the product, it will be wasted, it will be discarded off, and it will be ending up in a certain waste stream. We integrate electronics into new products that might not be as recognizable as electronic products as the typical electronic products like a television and a computer. When integrating products into a health patch, where will people throw away this product? We think it will be mainly e-waste stream, of course, if electronics are recognized, but it will also end up in the household waste stream, the municipal solid waste stream, called in scientific terms, the medical waste stream when having been in contact to the body, but maybe also other waste streams like compostable waste stream, automotive waste stream, maybe even in paper if we integrate into paper and textile. And I think there's little imagination necessary to understand that paper waste stream and textile waste stream will be really polluted with electronics. For the others as well, but we will concentrate now on the three first ones, e-waste stream, municipal waste stream, and medical waste stream, because we looked at what is on average worldwide these waste streams consisting of, and what is the potential to recover the valuable metals, especially valuable metals, scarce metals. And these are the numbers that we could compose. So e-waste is about 62 million ton per year. Municipal solid waste is much more. And medical waste, it was difficult to retrieve this number, is smaller compared to e-waste. And looking at what amount of copper and silver are in these waste streams, you see the numbers here. And basically only the e-waste stream allows to recover copper and silver. Again, these are general numbers. There are big differences between regions. These are the worldwide numbers. So it would mean printed electronics preferably ends up in the e-waste stream. Now we did experiments in Sustronics project together with Mirek, an e-waste recycler from the Netherlands, where we looked at their process, which is a typical e-waste process. So already explained by Mikko is the fact that PCB electronics, they are based on a rigid FR4 board with a lot of copper components. You see that on the top picture. And when these kind of products comprising the PCB electronics enter the e-waste stream, first of all, products are shredded, are smashed to allow the electronics to be set free, so that on the belt next to it, in the next phase, they will be separated from the plastics and the others. And if you look at PCB-based electronics, then of course they will end up in the bin with concentrated electronics that will go to the smelter for chemical and pyrolytic processes to recover the metals. The rest will go to the plastics recycling in basic terms. Now comparing it to printed electronics, which are typically flexible, larger area, more distributed electronics, as you can see in the top. When we did the experiments in the e-waste recycler process, we saw that the electronics, first of all, they're not shredded, similarly to the PCB electronics, but also the separation was not as efficient as for the PCB electronics, to say the least, not efficient, because the printed electronics ended up not in the bin for the smelter, containing all the electronics, but actually in the plastic waste bin. So it would mean it would pollute the plastics recycling stream, which is very much unwanted. And this is because the separation of the electronics was not occurring like it should, and also the selection was not occurring. We are aware that e-waste processing is completely focused on PCB, so most probably e-waste processing can be adjusted for printed electronics. But we did also in the project an experiment with waste from the project itself at a special recycler, the company PMR from Remondes Group in Moerdijk, that recycles specific silver-containing waste from photographic films, etc. And we gave a batch of our waste, and that showed that 95% recovery of the silver being present in the printed electronics was easily done. So we think that for a good e-waste stream, the modularity is key. Get the electronics out earlier before you get into the waste stream, so that you can concentrate the printed electronics in a separate batch. So this is becoming then the overall scheme. The segregated stream would be the best possible way to recover the metal, but of course asks for a collection scheme, society, consumers to cooperate and make sure that you have an offering to the waste stream that is more pure when it comes to printed electronics. Then the next finding of the project is that if you look at more sustainable materials, this picture was also shown by David, we applied the knowledge that more recycled and other materials, reducing the fossil-based content, going to bio-based, going to paper, really reduced the environmental impact. So we created a smart wound dressing based on paper with carbon inks. So carbon does not represent a similar value as silver or copper, and for that, completely new waste streams become possible. So we did a study to study the biodegradation of a paper-based electronics piece containing carbon and as comparison, the copper and the silver particle inked. And you see on the left-hand side, this paper was introduced with some electronics into a compost mixture, and under industrial composting conditions, you can see that in 8 weeks' time, the paper was completely biodegraded. When carbon was present, the second row, you see that also the paper was completely biodegraded. With silver containing particles ink, it was reduced. You still see some of the circuitry present, but with copper especially, the complete circuitry after 8 weeks was still present. And on the right-hand side, you see the CO2 evolution of the biodegradation, which is indicative of the microbes producing CO2. And you can see on the bottom that in blue, the paper plus copper completely inhibited the biodegradation of the paper. So we think this is a very worrisome result. Especially copper inks, they show that they inhibit the biodegradation. So imagining waste not being in proper waste streams, but landfilled, we think that this is also an effect that should be studied further. And we tried to analyze the reason for this, and we found that the copper ions present in the compost were much more in number than the silver ions, which makes sense because copper is more readily oxidized, less noble, and creates more soluble salts. So in conclusion, we found that printed electronics are not compatible with the current e-waste management. Modularity would be important to, first of all, have the R strategies, recycle, integration, etc., but also to make sure that we have a separate batch of printed electronics for recycling, because we have this alternative waste stream that gives the 95% recovery rate, but ask for installment in society to enable this. And our last conclusion is that we think that more research and development is needed for a better end-of-life destiny of printed electronics. And I hope that you agree with my last conclusion. Sustronics, in the end, is design your electronic product to serve your preferred waste stream of electronics. Thank you.
Thank you, Margrethe, and thank you for the clever acronym explanation. Reminder again, if you have any questions for the presenters, just write them in the chat and I will facilitate after the last presentation. Our next presentation will be given by Dr. Armands Ankans. He is from Elektroniska und Datorsignatno Institute. He can say it better after a while. He holds a PhD on body sensor networks for surface shape reconstruction. And for the past 11 years, he has been with the Institute of Electronics and Computer Science, specializing in the prototyping of wearable sensor systems and real-time data processing algorithms. And in this Sustronics project, he led one of the tasks, namely task 2.6, where there were sustainable software functionalities developed. Welcome.
Hi, thank you, Lisa, for the introduction. So, hi, I'm Armands. So in the project, we partners developed 19 software functionalities across 8 pilots, and I thought it would be fitting to categorize them according to circular economic actions they enabled. And I came to 4 categories or pillars. I will call them pillars: dematerialization, lifespan extension, resource management, and end-of-life ecosystem layer. Dematerialization is about doing more with less physical hardware, and we had several software functionalities that address this, and here are some examples. For example, partners developed a mobile application for in vitro diagnostics, which completely eliminated manual documentation. And on top of that, reduced the patient travel needed to do the test. Other example is control software for Philips X-ray system. It enabled the hardware design that led to 600 kilograms of less material used in the design. So it's not directly circular economy, but it means less material needed to recover at the end of life. So it's a big win. Also for vault file system, which used smart erasure encoding to cut in half the storage required for edge devices to operate. So meaning that it reduced the amount of electronic devices needed to manufacture, as well as reduced the energy needed to operate. Lifespan extension pillar is about keeping hardware in the field longer. And here are some examples. For example, control software for Philips X-ray system used AI to turn off the generator when it's not used, resulting in prolonged use of the hardware, preventing hardware wear, and for smaller devices, lower wake-up transmitter drastically reduced the energy consumption for wearables, and in particular in pilot for wound dressing. And smart patch data collection proved that using machine learning signal processing can keep the patch in the field 18% longer. And the resource management pillar is about optimizing the use of disposable products. And in the project, there were two great examples for incontinence products and smart wound dressing when using the software and artificial intelligence, they moved from fixed schedule care to predicted needs. So they prevented the changing dressings and incontinence products when they were not needed. And the fourth pillar is about end-of-life ecosystem. And in our project, it was addressed by digital product passports. It's critical in product recycling because we cannot recycle if we don't know what the product is made of and who owns it. Here in the slide, you can see some of the functionalities of the digital product passport was developed for this functionality. And this is related to personal health devices. So this was a quick overview of the circular economy actions that were addressed in the project. But I wanted to note that software can optimize only what hardware allows, and that is one of important learnings. And here, so to work in this work in the real life, we cannot look at the software only. We have to look at the broader picture. At least we have to look at the hardware the software is running on. So it's here I will stop and allow introduction of Max and Echo to design framework, which will explain how to do it. So thank you.
Thank you, Armand. This is indeed a different perspective for sustainability from the software side. And now we are actually already at our last speaker today, Dr. Max Marvede from the same Fraunhofer Institute as David, where he leads the Circular Design Lab. He has a background in economics, physics, and philosophy. Through applied research, his team helps companies to develop circular product service systems. And he will now tell you about the Eco2 design. Welcome.
Thanks, Lisa, for the introduction. Hello, everyone online and offline. So yeah, we heard a lot about different topics touching on sustainability from different perspectives. And right from the start in the project, we wanted to also integrate this into one common framework. And how did we do that? We actually started with drafting an eco-design process at the beginning of the project that we followed along the project, aligning those activities we've seen already in the last presentations. There was a lot of communication between the different tasks and activities, partially well communicated, partially not. It took quite a while until everyone had the same understanding what sustainability means. But at the end, I think we got everyone on board and we're very successful in driving sustainable electronics. And what we did also on the research side, we heard from Ulla, for example, reflection on how LCA influenced the business modeling, how LCA influenced the technology development for Margaret here, and also how software supported all this. And so in the final step, we integrated this into a common design process framework called Eco2 design. And I will shortly present this. You will find all the results in a public deliverable 4.5. It's about 20 pages. Just the process description is about 20 pages long. So this will just be a short glance on the process framework. We separated the process into 5 phases. Of course, they're interlinked and partially iterative. Maybe to mention that within the project, we just basically ended up at the product service system development because we didn't bring the products into the market, which would be then start in the piloting phase and the validation adaptations. So the first 3 phases are really based on the work we did, and the last 2 phases, the process framework description is more on the literature basis. So we have those 5 phases, but also 5 different stands in that phases, which are interrelated. And that is circular business model development, which we heard from Ulla, then creating a value network to realize the circular solution, doing the environmental assessment to support the technology development, but also the business model development. And from Armand, we heard how software and data can enable those circular solutions. I just want to highlight a few things. So for the environmental assessment, we understood and we saw that it's very important to have a baseline assessment to know where you stand, where the hotspots are, and what your targets are. So this is very important to start at the beginning with that baseline. And especially for new technologies, you don't have the data available, so you have to start with what you have. And along the way, along the development steps, you gain more data, you get empirical data out of the labs, and you can use that to refine your models and improve your assessments. So those assessments were actually used also to drive the technology development. And what we also saw, what was already mentioned before, is that this iterative process was really relevant, that we started with a proof of concept with available technologies to show what works and how it works, the functionality first. and then start to improve on the sustainability side from there on. So introducing new materials, improving the processes, and still keeping the functionality we realized with new materials and new processes. Then you have to align the eco-design with the business model development. So you have to think which sustainability strategy on a product level adds to value in the ecosystem. So either for any partner in the ecosystem, so for example, a recycler, but of course, very important for your end customer. So which sustainability strategy or our strategy from the circular economy is adding value in the system, and aligning both brings benefit, of course, to the whole system, but also enables circularity. And on top of that, it's very important to create this partner network around your circular solution. The partner network allows the circular solution to happen. And for that, you need to create common strategy, common KPIs, common governance structures to run this network. And last but not least, what you heard from Armand, of course, you need to think which data do I need to assess sustainability and circularity, but also which data do I need to enable the business model? And who do I share that data with? And who is creating that data? And how can you create the governance system of managing that data? Of course, all these parallel strands are interlinked, and there's many interdependencies on that, but you see that then in the deliverable. So to complete, we also created a white paper, which will be published soon, where we also identified call to actions for different stakeholders. For example, industrial companies, what I already mentioned here, that we think that integrating lifecycle assessments in the early design phase actually also helps the business. And of course, what we heard from Margaret, that also integrating end-of-life consideration as an early design driver also supports sustainability. On the research community side, we experienced live in the project that using those eco-design or co-design methodologies is benefiting everyone. But we also see that there's still work needed to create SEA methodologies, specifically, for example, for end-of-life strategies, where we don't have yet specific recycling technologies available for new materials, no new components or new products. For the policymakers, we support that the extension of the product regulations to also new type of technologies, and we see there's still the need to standardize sustainability and circularity assessments. And cross-cutting innovation, also in the product, we experienced that balancing innovation with environmental and social responsibility brings a real benefits, specifically to the pilot use cases and the companies within the Sustronics project. So with that, I would like to hand over to Lisa for the Q&A session. Thanks a lot.
Thank you, Max. Very interesting new methodology approach. So there has been a couple of questions in the chat, but I will first start. There is also questions with, is the recording and the presentations going to become available? As written in the chat, the recording will become available at Sustronics website and also in our YouTube channel. And then the presentations will be also shared with those who have registered for this webinar. But then about the questions in the chat. So first, I think this is was directed to Mikko. This is more like a comment, but perhaps you can comment on this. So I suppose right now in the health sector, we do not draw any sustainable lines. We throw away almost everything. So I guess this is a question about, does it really matter to do more sustainable if everything is thrown away?
Yeah, I think that is the case nowadays, though I'm not expert on how things are done in hospitals. But yeah, it might be now done like that, but it's also that it could be done different ways in future. But anyway, if you throw away something which has less sustainable, is more sustainable than something which is less sustainable, it's also the right way to go.
Okay, thank you. Then the next question is to Margrethe. So how can we create a new different recycling stream for printed electronics?
Well, the best example I think I already gave in my lecture is to collect printed electronics as a separate stream, because there is this industrial recycler able to recover 95%. But we are aware that, of course, that asks for a collection scheme and cooperation of consumers and society. So that would be the best. Or redesign electronics to allow another waste stream, like, for instance, the compostable waste stream. Wouldn't it be nice if you're allowed to throw away your paper-based electronics just in the green waste? Because we know it will not harm and it will only feed the composting process. But that asks for a different design of electronics. And that's exactly what we try to accomplish in Sustronics.
Okay, thank you. So then the next question is to Armands. So at scale, I would say the impact of the software built to manage sustainable electronics from a sustainability point of view is very minor. It is not as if we are doing heavy processing on any data. What made you choose EC out of many options for storing data safely and efficiently? Did you split the fragmented data to multiple locations? I'm not sure, can you answer, but you can read it here.
Thanks. So there are multiple questions, right?
It's just appeared.
So sorry, I'm slow reader. So yeah, it's an interesting question. But if I got it right, so manage sustainable electronics was. So yeah.
We can't hear you. You are on mute.
Perhaps we pressed that one.
Yeah, I would like to redirect this question maybe to my colleagues. It's about storage. I guess it's about file vault system. Maybe they can answer the question better, but I'm not sure if anyone is here right now. So sorry.
Yeah, that's fine. because Armand, of course, presented the work from lots of other people, so he is not expert on all of the details. But then the next question is to Max. How Eco2 design framework is linked to SSBD, safe and sustainable by design methodology? Have you thought about that? And I guess this relates to this, why these frameworks are not aligned to harmonized decarbonization targets.
Yeah, thanks. Very interesting question. So to be frank, we didn't use the SSBD framework as such in the project. I think the SSBD framework covers both, the avoidance of the use of hazardous substances or toxic substances, which we also addressed in the project, but not as priority. I think the priority in the project was reducing the environmental impact. So we had the focus on the sustainability side. But of course, it makes sense to also integrate the safety side a bit better in the framework. And why are these frameworks aligned to harmonized decarbonization targets? So maybe one answer to that is, of course, one of the main indicators we looked at is CO2 equivalent, so GWP, reducing the global warming potential of the products. But we also looked at other indicators like resource depletion, for example. So here, I think maybe the answer is not to look only at one target, because if you have this like narrow focus, it could mean that you improve or reduce the global warming potential, but increase another impact category. And so from our perspective, it makes sense to look at several impact categories and try to improve at least one of those, but not worsen the other ones. So I would say from the sustainability point of view, as a summary, safety of the materials, but not only looking at decarbonization, but also looking at resource efficiency, toxicity, and many other indicators make sense.
Thank you. And I think this question is still for you, this about the value network. So which KPIs do you propose for electronics? Comparison with standard, what is missing, what need further development for electronics?
Well, can you answer that?
Yes, so actually, this is a very interesting question and valid one, especially because we were creating new kinds of products in Sustronics, products that don't yet exist on the market. So you have the component of the digitalization benefits and, saving in the logistics. So you need to maybe think of it as a way of selecting the KPIs depending on the stage in which you are in the product development process. So in the beginning, you track just that you are actually applying to some design principles, and later on you go into this kind of a more market oriented and large scale deployment kind of KPIs, and you can look at the energy efficiency in manufacturing and the amount of waste generated. So I would say they evolve as the products are created and developed. And actually that's a interesting research topic that we're actually focusing also in my research team. So please contact me again later.
Thank you. Then we have one question, not sure who this is specifically addressed to, but what are the ways we can involve with skilling and training in printed electronics? Anyone has any thoughts on this one? Marguerite, yes, please.
There are several research institutes involved in the Sustronics project. So I guess all of them, including the startup companies producing printed electronics, are willing to explain about the technology and make sure that people will be up and running on printed electronics, despite the challenges that still exist.
Thank you. And then there was a comment, not necessarily a question. This forum should suggest and propose some well-targeted problem statements to take up for this community ahead. So as Max mentioned, we are preparing a white paper with the list of recommendations for the different stakeholders. And we will publish this white paper before the end of May. And if you keep following our website and LinkedIn, then you will be the first to hear when the white paper is out. And of course, we will also inform there when the recording of this event is available. We also have a couple of people in the audience here. Is there any questions you would like to state? Okay, just no, they won't hear you.
Hello, actually I have a question regarding the LCA methodology that you have just mentioned. And my question is about what kind of software you used, or have you developed any software during, in your project, or what kind of software you recommend for this kind of analysis? I mean, for in general, electronic industry or electronic manufacturing. Thank you.
Right. Thank you. Now I can answer from here. So first, which software have we used? Well, within the project, the LCA has been done by different organizations. So it wasn't only us, but also others. And in the end, each of us works with different software. So we work with Sfera, but others have been working with CIMAPRO. And then, of course, here, the segueing a bit to the question of which do we recommend. Here it's also a bit the differentiation between the software and the database. That's a bit that's a bit the issue, right? So for electronics, it depends. It's hard to make a recommendation. Depends on what you're going for. There are certain databases that are better. Let's say if you're modeling a product, some databases like the Sfera database, for example, they have like a very comprehensive set of like ready-made components. But then equipment is also very good. Let's say for like chemicals, materials. So it really depends. It's hard to say. There is no one solution fits all. And then depends on what you're looking at. If you're looking at carbon, for example, there is also many publicly available sources that you don't necessarily need to pay for. So it's hard to say. It depends what exactly do you need to look into, and yeah, what's also how much you can afford in the end. But let's see. I mean, the hope is also that there will be more work in this area. Not so much in the software direction, but more in the data direction, so that there is also data freely available for more people and on more topics. There is some a good resource to check what's out there is the OpenLCA Nexus website. They do have like a list of different databases, both the ones you have to pay for and the ones that are free. And there it's good to check what's out there that may be useful for different people and how available it is.
Thank you. And in the chat, there is also questions how to collaborate with Sustronics. So I provided my email, so you can be in contact with me and I will direct you to the correct persons, depending on your topic. I know quite well everyone in the consortium. Any more questions from the audience or not in the chat either? So then I would like to thank you all for participating. So especially our speakers, thank you for taking time to prepare these excellent presentations and being present here today. And of course, thank you for the audience, both here in Barcelona and there online. So it was a pleasure hosting this webinar today. And yes, keep following our website and LinkedIn for more updates. And the recording will eventually become available. So thank you all and have a nice day.